here. Okay, so today's MRI Lecture 2. So before we start, are there any questions on the course? Where we're going from Lecture 1, anything? Okay. So I think most people did the MRI pre-lecture quiz. I think everyone did pretty well on that. So we're not going to cover it in too much detail. I'll touch upon it a little bit in the lecture, and we'll go from there. So today we're going to review some of the material we did last time, and we're going to cover RF excitation, review, and some new material. We're going to talk about the transverse and longitudinal components of the magnetization. We'll introduce you to what relaxation means in the MRI context. We'll get to the Bloch equation, which is the governing equation for MRI, and then we'll hopefully get to K-space and talk a little about encoding with gradients. We may or may not make it to the MRI signal equation. If not, we'll get to that next time. Okay. So there's a lot of components that you need to understand MRI. So we're sort of building them up slowly. Okay. So just to remind you, last time, most of the lecture we talked about the purpose of the main magnet, which is the B0 field. Okay. And that's job is polarization. Okay. So on the quiz, that was sort of the giveaway answer. It's just the main job of B0 is to do polarization. The field we're going to talk about mostly today is the B1 field. Okay, so that's the RF field, and that has the main job of that is excitation. Okay, so putting energy into the system. Later on, we'll talk about the gradient coils, which do encoding, and then the RF on the receive side does what's called integration. So just to remind you, in the presence of no external field, the magnetization sort of is randomly oriented, okay? And so there's no net magnetization. In the presence of a external B field, then there's a preferential direction for the magnetic moments to be aligned with the external field, and that creates this net magnetization. So there's a lot of still random orientations, but overall, there's a little bit of net magnetization, okay? That magnetization is proportional to the B field, okay? Which is why people build bigger and bigger magnets to get that magnetization bigger and bigger. It's because that's your source of your signal, okay? So that process of creating that net magnetization is what's called polarization, all right? The other important thing that we talked about is the concept of precession, okay? So the magnetization, the spins have both a magnetic moment and they also have a angular momentum, okay? So if this is the spin here, let's say mu, if it didn't have angular momentum, then it would just go back to its equilibrium position, would be aligned with the B field, okay? But since it has net magnetization, the governing equation of motion is d mu dt equals mu cross gamma b. Okay, so you go back to your high school math, and mu cross b is the right-hand rule, right? And so that means that d mu is going to be this vector. In this case, you can imagine it pointing right out of the board, and that's going to be always perpendicular, tangential to the circle. Okay, so this basically is causing this magnetization to precess. That's the precession that we talk about. The most important governing equation there is omega equals gamma b, or in terms of cycles per second, it's basically, okay. So typically, I tend to remember things in terms of hertz. So this would be, for hydrogen, is 4257 hertz per Gauss, although in the book they use 4258 hertz per Gauss. So just in the homeworks, I'll tell you which one to use, just so you know which one to use, okay? So remember, the Earth's magnetic field, the B naught in the Earth's field is around half a Gauss, right? And so on the homework that's posted now, you have an opportunity to use your iPhone or your Android to go around and measure fields around San Diego or your house, whatever. But right now, sitting in this room, half a Gauss times 4257 gives you about 2000 hertz. Okay, so that's sort of the other quiz question that you would have gotten. Okay, and so that means 2000 hertz is right in the audio frequency band. Okay, so that means actually if we hooked up, made an MRI system here, we could actually listen to the spins processing in the audio band. And in fact, that's been done here. So this is a university project, I think out of Pakistan, where they actually built an Earth field MRI and are basically listening to the MRI signal in the audio band because it's about 2000 hertz. Does anyone know what note that is? I don't know, it's like an A or something like that. Yes. Yeah, we'll get to that. No, what frequency, what note is an A? 2000 hertz, is that like an A? Huh? What was it, a B? Okay, so it's like a B. All right. This is actually the Los Alamos one. This is some Los Alamos researchers who actually also designed an Earth's magnetic field MRI. This is actually an NMR system, not to do MRI, but to look at chemical. And the idea is that if you have a natural disaster, you could take this out into the field. You don't have to have a magnet. You can just put in chemicals and detect. I think they said they could detect about 40 different like toxic chemicals out in the field. Okay. I think on extra credit, I just put this figure here, just because if you're going to do the extra credit on the homework, you're supposed to go measure the fields back here where there's a magnet inside here. And so this is just a view, just remind you, if you're going to do that part, this is what the view should look like. So you're going to measure the field along this wall. Okay.
I visited there for last Saturday, and I found that the field is fluctuating is not very stable.
Yes, well, basically, without getting into all the physics of it, there are naturally occurring magnetic fields from the geomagnetic sphere. So all the time there are fields happening. So there is a static field. And so if you average over like a minute, that's what you, or, just average, give it the average. But all the time, basically the sun sends out particles, okay, and they hit the Earth's magnetic field, and that creates a lot of disturbances. And so there's lots of weird, interesting things. So there's lots of fluctuating magnetic fields all the time. Okay. Okay. Okay, yeah. So there's a lot of interesting thing about the magnetic fields in the environment. So, but don't worry about that for this course. Okay.
I also measured right on the wall, and it's above 5 Gauss. Is that normal?
It is. I mean, if it's very close to 5 Gauss, shouldn't matter. Yeah. Okay. So that's just a review of the B0 field. So that's pretty much all we're going to talk about the B0 field. Okay. In terms of, we assume that we've got a magnet that creates a polarization. That's a signal we deal with. So we're going to spend most of the course talking about the RF field and the gradient field, because those are actually what allows us to take the image, and that's where all the action occurs. So typically when you buy an MRI system, you don't mess with the B0 field. You just buy that. Okay. And what you're allowed to do through the software is, we have our grad students and staff scientists, they write programs, and we control the RF field and the gradient fields. And that's what we get to control. So just to remind you, spins process around B0, and if you want to use the left-hand rule. So if the B0 field is pointing this way, or any B field, the spins will process the way your fingers go with your left hand. Okay, so that's the direction of precession of the spins. And so in this movie here, you see, if it plays, you see the spins processing around in the correct direction. And now you see them, we're tipping them away from their equilibrium. Okay, so the net magnetization is going away from equilibrium. And the idea here is that this allows us to have a signal that's easier to measure. Okay. And also it's going to allow us to create lots of different contrasts. So the key is there's going to be a weak B1 field that we're going to apply that helps us rotate our magnetization to get it away from its equilibrium position. Okay, so to remind you what that looks like is this is showing the magnetization. So this is showing the magnetization. So it's aligned with the B0 field. So imagine B0 field is going this way. Okay. And then this is the magnetization. And if it's just a line like this, then it's sort of, if you imagine, if it's perfectly aligned without getting into the quantum mechanics, you can imagine it's just going like this, right? Just processing out to an axis. But if we tip it away, then it's going to process like this. Okay, so you can actually see the precession. All right. So that's what we're going to see here. The blue is the B1 field we're applying. And basically the magnetization is tracking that B1 field. So this is the B1 field. All right. Now, as we talked about last time, the key is that has to be applied on resonance, okay? The spins want to process at a certain frequency. So if we apply the B1 field at a different frequency, the spins aren't really going to respond to that. Okay, so that's shown here, where you can sort of see the spins just sort of stay here because they're not their precession frequency is not such that they can absorb the B1 energy that we're putting in, right? So it's sort of confusing to think about things spiraling down all the time. So just to remind you, we will be doing everything in a rotating frame of reference. So everything we do in this course, basically from now on, is in a rotating frame of reference when we're looking at MRI equations. So instead of this complicated picture here, where we have to imagine the spin spiraling down, we can just imagine that here's the B1 field. Okay, so the B1 field's pointing this way. So if a magnet, it's the precession is going to be like this way. Okay, so that's what you're seeing here. The precession is going that way. So my thumb is pointing this way, right? So it's going to cause a precession to go around that B1 field. Okay, so that's what gives this flip angle. And then the idea is if you're going at the same rate of precession, then it's almost like as if the B0 field doesn't exist, right? Because in the rotating frame of reference, you're not rotating around. So there's nothing that you're processing around. So in the rotating frame of reference, the B0 field is basically effectively non-existent. Okay. So in the rotating frame of reference, instead of having to follow that spiral, your life is easier. You can just imagine the magnetization just tipping down away from equilibrium. Okay, so that's a much easier thing to think about. So this is another picture of that. So just showing that the effective field is B0. There's a B0 minus omega gamma component. And so when omega equals gamma B0, this goes to 0. Okay, so basically there's when you're on resonance, the main field, it's almost as if it doesn't exist. Okay, it's the same thing as if you were looking at something on a merry-go-round and it looks like it's rotating. The moment you get on the merry-go-round, not everything in the merry-go-round appears stationary to you. Okay, so let's look at flip angle. So the first MRI parameter we're going to remind you about is the flip angle. And so on every MRI console, when you look at it, you will see a field for the flip angle. Okay, and so it's a very important parameter that we'll talk about later. And the flip angle is essentially given by the integral of the precession frequency integrated over time, where that precession frequency is gamma times the B1 field. Okay, so it's a very simple formula, but you can actually do a lot with that formula. Okay, so just to remind you, this was the example we did last time. So this is an example of what's called a hard pulse. So it's on for 400 microseconds. Okay, it's got some B1 amplitude, right? And so what we want theta equals pi over 2. So we just say, okay, well, this integral of gamma B1, right, is just going to be B1 of S of ds, time varying, but B1 is just a constant. So this just equals gamma times B1 times my tau, right? And all that has to equal pi over 2. All right, so then we can solve for B1 from there. All right, so yes. Oh, you're typically given what gamma is. So gamma, so here, like gamma over 2 pi. So typically what I remember is gamma over 2 pi equals 4257 hertz per Gauss. That's the number I just keep in my head. The book uses 4258 in the book. Okay. So, yeah. you'll be given that on all the problems. So like on the homework set, actually, that is it posted? Yeah, I'm not sure if it's posted on this homework. There'll be another homework posted on Wednesday. You'll be told, but I think it's actually you're told a gamma 2 pi on this one, but I don't remember. Okay. Okay, so let's have you guys work on this question. So consider an RF pulse of the form A sinc T over T. So what does it look like? It looks like this. Okay, and then this is amplitude of A, and the first 0 is at T equals 250 microseconds. Okay, and in this case, to keep things simple, assume gamma over 2 pi equals 4,000 hertz per Gauss. Okay, so I'm going to give you guys a couple of minutes. Your job is to figure out what A to get theta equals pi over 4. Okay, so feel free to consult with your neighbors. We'll set up a poll online, and then in class, we'll just do an audio poll. So go ahead and take a few minutes and think about that. I give you about another minute and just sort of think about how you might go about this problem. Okay, so let's take a poll in class. So at the count of 3, just say very loudly what you think the right answer is. Ready? 1, 2, 3. That was not very loud. Let's try again. 1, 2, 3, go. So I heard D, E, F. Okay, so I think there's some diversity of opinion. So probably we need to go over this problem. So remember, the theta is just equal to gamma times B1 of T dt, right? Okay. So that means we want to take the integral of gamma of A sinc t over t, right? In this case, we'll assume minus infinity to infinity. Okay. So who wants to integrate a sinc function for me? So what should I do if I don't want to integrate a sinc function? What property should I use? Anybody? Anybody online? Okay, so should I pick someone to integrate the sinc function? Who wants to volunteer? Sine, okay. So we could take sine. Okay, so let's try that. Okay, so what should we do next? I can't hear you. Can you speak more loudly?
Sorry. We can't just put the pi p over the determinator based on
The pi t over t? Okay, so how would I integrate this function?
function call.
So how do I integrate? So would I do integration by parts probably, right? Does everyone remember integration by parts? Who wants to integrate by parts? Anybody? No. Okay. Yeah. Okay, so we could spend maybe 5 or 10 minutes doing this, right? But I'm really lazy, right? So what property from the Fourier transform could I use? Yes, go ahead. That's possible, right? So that's one. So we could do that. Yeah. So let's think about that. So we know that that's a good thing. So what is the Fourier transform of sinc t over t? What property do we need to use? So it's going to be a rect function, but what is it going to be a pure rect function, or is it going to be something slightly different than our actual rect function? Scaled rect function. Okay, so what's the scaling theorem tell me that this rect function, this sinc goes to? Right, t times rect of tf, right? Or let's say f is my frequency. Okay, so that's the scaling theorem. Okay, so great. So I have that the Fourier transform of sinc is t times rect t of f. So that's good. So now what do I do with that? What frequency do I care? So I need to put in f. Like what value of f should I use? Yes. Okay, so possibly I could use f equals 1 over t. Okay, that's one possibility. Any other suggestions? Okay, let's look at this integral, right? That's some function times dt. So that's some function times e to the j 2 pi something, right? So what goes in this parentheses? What gives me, what e to the j 2 pi something what gives me 1? Yeah, 0. Yeah, okay. So if in doubt, 0, 1, and pi are pretty good guesses for any engineering problem, or e, right? So yes, so basically this is just e to the j 2 pi times 0. So that means I would pick f equals 0, right? That's just the Fourier transform at f equals 0, that integral, right? So anytime you see a really nasty integral, think about whether you can take the Fourier transform of it, because then you just evaluate it at 0. Okay, so we're going to see this later on in terms of Fourier transforms. So then this just equals t then, right? At f equals 0, right? Okay, so I know, basically, I know that the area of that sinc function is just t. So that's pretty cool. So then I can just say, well, I have gamma times t times a equals pi over 4, right? So that's equal to, so a is going to be equal to pi over 4, and then gamma is 2 pi times 4,000 hertz per Gauss. And then I have 250 times 10 to the minus 6 seconds, right? The pi's cancel out. I get, what do I get on the bottom? I get like 1 over, what is that? 8 times 4 is 32 times 10 to the 3 times 250 times 10 to the minus 6. I think we end up getting about 0.125 Gauss. I think that's the right answer. Okay. You guys can think that. So I think F is the right answer, but you can sort of you can verify that for yourself. Yes.
There's actually another way dealing with this kind of integral, can treat it as a complex function, and then use the residual theorem on the complex plane.
Yes, you could do that, but for this course, just use Fourier transforms because we know the Fourier transform of a sinc. So the reason we show this is because right now, all across the world, this very function is being played out on MRI machines everywhere. Okay, this sinc function is really integral to MRI, and we'll see why later. So this is a very important function for us to know about, and we'll be using the rect and sinc functions all throughout the course. So just make sure you understand those two functions, and if I scale a sinc function or scale a rect function, know how to go back and forth. Okay. Any questions? All right. Okay, so let's talk about free precession. So remember, here I'm using m. So m is now like over a voxel, m is just sort of the integral, of mu over some volume. Okay. So I'm taking all the spins within the volume. And since everything is linear, I can assume that the m is just will precess also. Okay. So in any given voxel, we're looking at the magnetization that's precessing. And the equation of motion is just m cross gamma b. Okay, so it has the same form. And so now what we want to do is start writing out what that means mathematically. Okay, so hopefully some of you may remember from high school again that it's just equal to the determinant of this thing. Okay, and so you can write that out. The determinant just equals that. Okay, so that's how you would write it down. And you've got this I, J, and K hat are your direction vectors telling you the different components of your dm dt. Okay, so this is basically a vector equation, right? Vector differential equation. Okay, so we can write it out like this. So that's just saying that I write at each component, the mx, my, mz. I have to break it out into different components. And then it turns out it has this really nice way the way to think about it is it's just this, the magnetization here multiplied by this matrix here. Okay, so basically you can convince yourself if I take these two things together, I'll just get this. Okay, so that's just a matrix multiply. And so this has a nice, so you basically see all the B fields are in the off diagonal terms, and the diagonal term is all zeros, right, for now. So, and then initially we're going to focus on the case where we only have a BZ component, okay? We're just going to initially focus on where we just have a B0 field. And by convention, we always assume in MR that the B0 field is along the Z hat direction. Okay, that's just the convention we pick, all right? Okay, so we're going to briefly review phasors, just to remind you again, because we will use phasors a lot in MR. It's essentially the way we think about MR. So just remember, we have Euler's theorem, e to the j theta equals cosine theta plus j sine theta. Whoops, I didn't mean to do that. So just a reminder what that means. If theta is equal to 0, you're pointing there. Theta is oriented, this is positive theta, right? And this is negative theta, right? So theta minus pi over 2 points that way, theta pi points that way, theta pi over 2 points that way. Okay, so just get, that's basically just the sign orientation we use for theta. All right. Okay, so let's take a look at this. So I have this equation here, and now let's just assume that B just equals B0 in the Z hat direction. So I only have that Z hat component. So now you can sort of see only the mx and the my terms are coupled, right? The dmzd term is basically just equal to 0, right? So this implies dmzt dt equals 0. Okay, so that means the m sub z component is not changing with time. So instead of dealing with two equations, we're going to come up with a nice little trick, which we use in MR all the time, is we're going to define a complex vector where the real part is mx and the imaginary part is my. Okay, so this actually is just a nice way of not having to carry around two equations everywhere. Okay, so it turns out if you do the math, then it's like dm dt equals minus j gamma, this should be a j, sorry, minus j gamma b naught m. Okay, so this is now a very simple first order differential equation, which you all know the solution to, right? It's just an exponential. Okay, so we can say that the solution to that is just some initial condition times e to the minus j gamma b naught t. Okay, you can verify for yourself if you take the derivative of that exponential, it'll give you the right, it'll solve the equation. And then we notice that the gamma b naught is just my Larmor frequency, e to the minus j omega naught t. And we notice that this just means that theta equals minus omega naught t, right? So as a function of time, it's going to go like this. It's going to go clockwise. Okay, so oftentimes, you do have to remember, is something going clockwise or counterclockwise? And so the natural precession frequency is clockwise. But when we talk about gradients, we'll find that we can either go clockwise or counterclockwise. Okay, so you want to keep track of the sign of that precession angle. All right. Okay, so now let's talk a little bit about what happens when you excite magnetization. Okay, so the RF puts energy into the system, so it tips it away, right? And it starts processing. Okay, so in the ideal world where there was nothing happening, this would just process forever, right? But nothing lasts forever, right? So eventually it's got to go back to here. Okay, so that process is what's called free induction decay. Okay, so I put in this RF pulse, I take the magnetization from, this thing, and in this case, I'm tipping it with a 90-degree flip angle, okay? And then the signal that I get decays away. Okay, so the way I measure this signal is I would have, for example, this is the magnetization, and I tip it away here. It's basically time-varying magnetization, right? Okay, so this, from the point of view of this coil, it's seeing a time-varying magnetization, right? And so then from Maxwell's equation, we know that the E field is proportional to dB/dt. So this is going to generate an E field, okay, in this coil. And that's what we're measuring here. So that's shown by this little loop here, okay? And the NMR signal we see will oscillate at the precession frequency, and it will slowly die down, okay? So that's what we want to talk about for the next maybe 20 minutes, is that oscillation and dying out. So that's called the free induction decay. This is sort of what I just described with my hands. The receiver coils here, picking up this time-varying magnetic field, which induces an E field in here, which is something, that's what we essentially measure, okay? So the measurement device in MRI are just simple coils, okay? We don't need anything more fancy than just a loop of wire, okay? Okay, so now we're going to talk about relaxation. And the key to remember is we have to talk about two kinds of relaxation. There's longitudinal relaxation, what happens to the MZ term, and there's transverse, what happens to MXY components. Okay, these are sort of somewhat independent but somewhat related relaxation, so you have to talk about them differently. Okay, but we'll talk later about how they're related. But for now, just assume that you're going to have sort of a longitudinal relaxation that governs how this M sub Z. So in this case, M sub Z is equal to M naught. It's the full magnetization. When I tip it over, at this point, M sub Z is equal to 0, right? There's nothing in this point. So this magnetization is going to slowly grow back. Okay, so that's the M sub Z component. The MXY component, right now there's no MXY component, right? When I tip it over, now there's an MXY component, and that part rotates around and also it's going to slowly decay away. Okay, so there's two components you want to keep track of, and we'll look at that. And in your homework for this week, there's actually an exercise where you have to look at the relationship between the M sub Z and the MXY components, right? Okay, so let's start introducing some notation. T1 and T2, you will hear all the time in MR. Okay, everyone's talking about T1 and T2. Okay, T1 is the spin lattice time constant that governs how quickly you return to equilibrium in M sub Z. T2 is what's called the spin time constant. It talks about how quickly this MXY component decays away. Okay, so you can think of T1 as regrowth and T2 as decay. All right. So this is what it looks like after a 90-degree. So the governing equation is this. Okay, so you can sort of see this is going to drive you back. Basically, you're trying to return back to equilibrium. This differential equation is the dMdt is always pushing you back towards M sub naught. Okay, with a constant of T1. Okay, so after 90-degree pulse, you know, at T equals 0, we assume that M sub Z equals 0, right? So that's shown here. And then it exponentially recovers back to M sub naught. All right. So that's given by this equation here. So just an exponential recovery. We'll talk later about what that means, but for now, just realize that T1 is that recovery constant. And why do we care? It's because different tissues have different T1s, and that becomes a source of contrast then. Okay, which we'll see later how we make use of it. But this is just showing here as a function of the magnetic field strength, the different T1s and seconds of gray matter, white matter in your brain, muscle, kidney, liver, and fat. Okay. So whereas in CT, we're looking at different absorption coefficients, right? Different attenuation coefficients. In MR, we have a lot more coefficients we can look at. The first one is the one today is T1. So today we'll cover T1 and T2. Later on, we'll look at other things you can measure with MR. Okay. Okay. So that's T1. T2 is transverse relaxation. That's basically this MXY component. So we tip it here, it's got this, but this isn't going to last forever. And it's going to exponentially decay away such that that goes to 0. It has this very simple form here, right? This is just you all should know that this is just something that's decaying away exponentially, right? That's a first order differential equation that you've probably seen many, many times. So what it looks like is if I start with some magnetization here, over time, it just decays down to 0. Okay. So T2 is largely independent of the field strength. And you can actually show that T2 must be less than T1. Okay. In fact, that's what you're going to do on this homework. That's on the homework, you're going to show that this is true. Okay. In order for M sub T to be less than M sub naught. Okay, so for everything to make physical sense, and that's because things that cause T1 relaxation, we'll find out later, also contribute to T2. Okay, so T2 is, T2 typically, if you look here, these are on the orders of like seconds here, right? Like 2 seconds to maybe 1 second. If we look at T2, well, here's just showing, well, before we get that, here's what it looks like. You just have this T2 decay of your magnetization. You can sort of see here, these T2 values are very, very short. Okay, so in gray matter and white matter, they're down in the hundreds of milliseconds. The only exception typically is fluids. So CSF stands for cerebrospinal fluid. It's mostly water with some nutrients in it. It has a very long T2. And we'll see later how a lot of clinical, there's certain clinical protocols that make use of the fact that water and liquids have much longer T2s. Okay. So this actually then becomes one of the things that governs how quickly we have to do things in MR. Okay. It basically says the signal that we care about is only hanging around for about 10 to 100 milliseconds. So that means we got to collect the data quickly, because if we wait longer than 100 milliseconds, there's nothing left. Okay, there's no more magnetization that's oscillating around that we can pick up. Okay, so that's why there's this emphasis on speed that you actually have to acquire relatively quickly. Okay, so basically, this is just showing that getting a little, so if I tip the magnetization, I have this. What happens is the different spins in different locations start to get out of phase. Okay, so over time, they get out of phase a lot, so that their net magnetization decreases. And so that's really what's causing T2. We'll talk more about the physical mechanisms later, but for now, it's just know that it's caused by this sort of dephasing of neighboring spins, okay? Okay, so now we can put everything together in what's called the Bloch equation. So just a reminder, Felix Bloch was one of the discoverers of NMR. He won the Nobel Prize for this discovery along with Edward Purcell. So this equation is named after him. It is basically what governs all of NR. We're just going to take sort of a quick look through it. So remember, this is precession. So this means that magnetization precesses around, okay? Any B field that's there, it will precess around it. This is the transverse relaxation. This is looking at the I and J hat components of the magnetization in the transverse plane. So that's just the T2 decay. And this is just the longitudinal relaxation, things going back towards equilibrium. All right. So when we look at matrix form, what we see is now the diagonal has those relaxation terms. Okay, so the T1 only applies to M sub Z, and the T2 applies to MX, MY equally. Okay, so that's it. That's all you need to know. That's basically MR, what's happening with the MR signal. Okay, so then the trick becomes, well, what do you do with this, right? How do you actually make images out of this? Okay, this is telling you what the magnetization is doing. Now it's your job to figure out how to use this to create images. Okay. So let's take a look at this. Just to remind you, so that this is another way of writing the equation. The general form of the solution looks like this. We did it for saturation recovery. So that's when we have theta equals pi over 2. So we flip the magnetization 90 degrees. Okay. And then it just has this saturation recovery back to M naught. Okay. But we could also, inversion recovery, we could also flip the magnetization pi. I can take this magnetization and I can flip it all the way this way. Okay. And then it's going to grow back. Okay. And then it turns out, because I flipped it down to minus M naught, as it recovers, it's going to cross through 0. Okay. And as we'll see later, this turns out to be a really useful way of erasing some tissues. Like if there's something in your sample, let's say fat or water, and you're like, I don't want to see the fat or water there. You can actually apply one of these pulses. And if you acquire the data right at this point in time, that magnetization is not there. So you can play a lot of cool tricks in MR and sort of erase things you don't want to see. Okay. The transverse component, remember, we have a complex notation for it, and it follows this equation of motion now. So we already looked at this part. Now it's just got a T2 decay term with it. And so the general solution is just this e to the minus j omega naught t times e to the minus t over T2. So at t equals 0, we start off here. And we basically just, in the transverse plane, it's precessing and it's also decaying at the same time. All right, so that's the picture of transverse magnetization. Okay, so this is a nice graphic from Brian Hargraves at Stanford that sort of, I'm going to play it once, a couple of times just to show you. But essentially here you're going to see the transverse magnetization, and here you're going to see the magnitude of it. And then here you're going to see the longitudinal magnetization recovering. Okay, so what you notice is the transfer magnetization typically dies off much more quickly than the full recovery. Okay, so that's typical for most tissues. So once again, you can sort of see MXY is hitting 0 here, and M sub Z is still going up. Okay, so these are two different time constants, right? Okay, so this is sort of what it looks like if you were to plot in the Z, X, and Y components together. You start off here, and you're basically spiraling down this way, but at the same time growing up this way. But since this spiraling happens faster than this growing, you sort of end up with this sort of picture. And once again, this is the property you'll show in the homework. Okay. All right. So that's all we're going to talk about for relaxation for now. We'll come back to it later towards the end of the quarter in terms of how do we make use of relaxation to create contrast. But for now, any questions on T1 and T2? Anything in the chat? No. Okay. Yes, question. Yes, it holds true for any tissue. Yeah, you show in the homework that it's physically impossible for T2 to be greater than T1. Yeah. Okay, anything else? Okay, great. So we're going to switch gears now. So we've talked about polarization. We've talked a little bit about excitation. We'll also revisit excitation later when we talk about how do you do slice selective excitation. But for now, we're going to move on to the gradient coils because that's going to really be the bulk of the next few lectures. We're going to spend on the gradient coils and how we actually make an image. Okay, so we're going to go all the way from what was done traditionally, how most if it's done, and then we're going to go all the way up to how it's done today. So we're going to go all the way from Fourier to deep learning in like 3 lectures. Okay, so fasten your seatbelts. All right. Okay. So, and then integration will come at some point. Okay, so just to remind you, there are 3 gradient coils in most MRI systems. There's going to be an X gradient, a Y gradient, and a Z gradient. Their job is to create, for most systems, linear gradients in the magnetic field. People are looking at nonlinear gradients, but that for this course, we'll focus on linear gradients. This, once again, is a picture of what a gradient coil looks like. I believe this is the Siemens factory in Germany. You can sort of see very intricate designs, all basically computerly optimized with computer programs to meet the criteria. Okay. So the main thing is the underlying property is very, very simple. It's just precession. Okay. So remember, omega equals gamma times B. That's it. But we're going to use that very simple relationship and show how you can create an image with that by being clever with how you apply the gradients. So if all I have is a B naught field, then everything is going to precess at gamma B naught. Okay, no matter where it is. Okay, so if I have a uniform field, then everything precesses the same way. Okay. But if I want to make an image, I somehow need to make things at different locations act differently, right? Otherwise, I don't have any information about what's at different places, right? So the job of the gradients is to create this delta B that is a function of X, Y, and Z. So I'm going to change the field such that now omega, the precession frequency, is going to be proportional to something that depends on X, Y, and Z. Now, to keep things simple, we're just going to focus on X, Y in this course. In practice, sometimes we do X, Y, and Z. That's called, so we're going to focus on 2D imaging. So we just do X, Y, that's 2D imaging. Clinically, we do a lot of 3D imaging. It's the same principle, just a little more complicated. So if you understand 2D imaging, then 3D imaging is just the extension of that. Okay. Okay, so the physical intuition is this, that, and so we're going to say that X equals 0 corresponds to, in MR, we call this the isocenter. Okay, the isocenter is sort of the middle of the magnet. Okay, and so when you do a clinical exam, there will typically be like even a button that says advanced to isocenter. Okay, it just takes your sample right to the middle of the magnet. Okay, and that's where the gradient fields are equal to 0. Okay, so that's where at this point, everything precesses at gamma times B0. Okay, away from the isocenter is where the gradients can act. And so, for example, here, this is obviously a gradient in the X direction, and GX is positive, right? Because it's getting stronger with positive X and less strong with negative X. And so here, spins will precess faster because they're going to be at a field gamma B naught plus gamma GXX. And here they'll process slower because they're at gamma B naught minus gamma GXX, right? So the idea is when we could go and look at these spins. Some of them are processing very quickly, or some of them are processing here. These are going even faster, and these are going slightly slower, all right? Okay, so here's an example of spins, and so you can sort of see the ones at the edges are processing much faster, and the ones in the middle aren't processing at all, okay? And that's because we're in the rotating frame, all right? So instead of having to keep track of everything processing, we just say at isocenter, we assume those spins don't process in the rotating frame, right? Because they're right on resonance, okay? So we're only looking at the relative frequency reference to isocenter, okay? And you can sort of see, so here would be like an X gradient because the variation in the spin rate varies with X. And here we're looking at a Y gradient where you can sort of see things are varying in precession frequency as a function of Y. Okay. And you can even see if you look at the ends, things here are processing one way and the things at the other end are processing the other way, right? Sometimes they're going, on this side, they're going counterclockwise. On this side, they're going clockwise, okay? So essentially, if I reference something to here, if something's going faster, it will appear to be going clockwise. And if it's going slower, it will appear to be going counterclockwise, right? The other thing you can do is you can apply gradients in two directions, X and Y. And so you can sort of see here, the line here along a diagonal, everything is still because those are basically, there's no gradient applied there. But as we move off from diagonal, we're making spins process increasingly faster, okay? So that's basically the fundamental insight that Paul Lauterbur had in the early 70s, that if you apply these gradients, you can make spins process at different frequencies, okay? Okay, so let's do just to sort of, we're going to work through a problem from the book, problem 12.1, just to sort of give you a sense of what this looks like. So this is assuming you have a non-uniform magnetic field pointing in the z direction. B sub z equals 1 plus 0.5 z. The magnetization vector processes around the z-axis. Okay, at time t equals 0, everything is in phase. And then, so basically we have, for example, whoops, let's keep, sorry. Okay. So the idea is as a function of z, right? Oops, let's change the color back. We have b of z is increasing, right? That's b of z. Okay. So at z equals 0, they're processing at like 1 Tesla, right? Okay. And then at, we have to look at 0.25, 0.5, and 0.75, okay? So let's just say, for example, at 0.5, we would have b equals 1 plus 0.5 times 0.5 equals 1.25 Tesla, okay? So we're just saying that this is a field that's increasing in the z direction, okay? And so this spin here is going to spin faster than the one at z equals 0, right? So I have two spins. This one, I'm assuming, is not in the rotating frame of reference, it's not rotating at all, right? And this spin is spinning a little faster. So the question is, how long does it take for this spin to do a full 360 and be in phase again? So initially, these two things are in phase, right? This stays steady in the rotating frame of reference. This is going a little faster. And at some point, it's going to be in phase again. So that's what the question is asking. And then this one is at a smaller field, so it's going to take longer to come back in phase. This one's farther out, so it's in a much faster field, so it's going to come in phase much more quickly. Okay, so that's all that question is asking. So let's work through it. So we can say that the delta frequency, the amount of frequency that we're accumulating, is just equal to gamma over 2 pi times delta b. Okay. And that's just, remember, our delta B is just equal to 0.5 t from the problem. Okay. So that means that the frequency that we're increasing is just, let's see, this is at z equals 1, right? Okay. And so that the relative frequency that it has with respect to the isocenter is 21 megahertz, which is quite a lot. So this is just sort of a problem. So it wouldn't really exist in practice. So that means if my delta F is this, that means one cycle delta F times delta T should equal to 1, okay, to get one cycle of rotation. So then I could just solve delta T equals 0.047 microseconds, okay? And so that means that here, okay, at 1 centimeter, basically, if I look at the spin, it's gone all the way around. It's gone 2 pi around, okay? So that means if I only went half a centimeter away, in the same amount of time, that would only go pi phase around, right? It only, because it's moving twice as fast. If I looked at 0.25, it would only go pi over 2, right? And if I looked at 0.75, it would go 3 pi over 2, okay? And it's negative because we're going in a clockwise rotation, okay? So theta is less than 0, okay? So that's just trying to give you a sense of the fact that we're actually trying to look at the relative phases of these spins, right? If I have spins processing at different frequencies over the same amount of time, the spins that are going faster accumulate more phase than the spins that are going slower. They're going to get less phase, all right? Okay, so we're now going to sort of build up to actually how we would actually create the MR image. And this is, we're going to go back to the rotating frame of reference, which we've just already talked about, which is basically, we used to do, before this was hybrid format, we used to do this with people doing this in class. It was sort of a fun exercise. With hybrid, we're not going to do that. So I'm doing these virtual avatars for you, okay? So this guy here is, imagine he is a spin in some B0 field, okay? So he's processing clockwise. He's showing clockwise precession, okay? Is there someone online? Let's see. Okay. So he would be rotating in the clock. Whoops. Yeah. So he's rotating around. He's processing in the laboratory frame, but in the rotating frame of reference, he would just stay still. Okay. So basically, at isocenter. So Erwin Hahn was a famous professor at Berkeley who came up with the spin echo, which we'll talk about later. He has this nice quote that there's nothing that nuclear spins will not do for you as long as you treat them as human beings. Okay. So when we do MRI, oftentimes you see MRI physicists like thinking about what the spins are doing, right? And when we're already trying to think, okay, the spin's doing this or doing that, it's almost like you're trying to understand, you're sort of thinking what the spins would do. So here's the exercise that we used to do in person. Imagine each of these represents a spin, and let's say the spin direction is going this way, okay? So in a laboratory frame, they'd all be spinning around at the same rate, right, in a uniform field, okay? In the rotating frame, they stay constant, right? They're not going to rotate around because they're in the rotating frame. And this, whoops. This guy is at isocenter, okay? And we're going to imagine creating a gradient field that goes like this, okay? So this guy is going to be delta B is greater than 0, and here delta B is less than 0, okay? And so this one is going to spin relatively much faster than this one, and this one is going to spin in the opposite direction, and this is going to spin even more in the opposite direction. Okay, so the relative frequency of precession is going to go clockwise for the faster spins and counterclockwise for the slower spins. Okay. And so, for example, if we come back some later time and look at them, you can see this guy has gone pi degrees, this guy's got, or minus pi degrees, this this person's gone minus pi over 2, this person's gone plus pi over 2, and this person has gone plus pi. Okay, so they've rotated that much. Okay. And so you can sort of see here, let's call this delta x, right? What is the period of variation of those orientations? Do you see a periodicity there? Like how long does it take to go from one orientation to a person that has exactly the same orientation? Because that would be the period, right? So what is the period here? 2 pi, one answer, but let's say delta x is the distance between my people. So what is the period if in terms of delta x? For delta x, yeah, good. Yes, so that's where you have 2 pi, right? But it just takes 4 delta x to get 2 pi, so that's good. Okay, so let's take another step, okay? Now this guy's got another step, so his relative phase is minus pi. This guy is back to 2 pi. This person always stays at 0. This one is at plus pi, and this one is at minus 2 pi. Okay. So now what is the period? 2 delta x, right? Okay. And now we've gone one more step, okay? So now this one is at, sorry, this should be plus 2 pi. Minus 2 pi. This is now minus 3 pi minus, I guess, 3 pi over 2. Is that right? 0. This guy goes pi every step, right? Okay. Plus 3 pi over 2 and plus 3 pi. Okay, now what is the period? 3 delta x? 1, 2, 3, 4. Or 4 delta x. It's still 4 delta x, right? Yeah. Yeah. It's sort of a trick question, so don't worry about that. So I have 2 points that have a period of 4 delta x, right? This guy has a period of 4 delta x, and this one also has a thing of 4 delta x. What's different about those two rows? Do you see a difference between those two rows? So what about this person here versus this person here? Can you tell? I know it's hard to tell. It'd be easier if this was in person, but this person is facing towards you. This person, you're seeing their backside. So the relative even though the period is the same, the relative orientation of the spins is different. Okay. So we're going to talk about positive and negative frequencies. And so basically what you're seeing here is in one case, there's a positive spatial frequency. The other one has the same period, but it's the negative. It's sort of a different orientation of how the spins are going. All right. And then at this point here, we're back at the period equaling. Oh, so here's the question. What's the period here? Delta x, right? We would call this period delta x, but in the limit, the period would be, we would call this, so for example, this has a frequency of 1/4 delta x, okay? So that's a spatial frequency. Here, there's no variation. So we actually call this kx equals 0, okay, when there's no variation, okay? So basically, there's no variation, so actually, the period, you can imagine, is infinite, okay? So in this discrete example, you could say, well, it looks like it's delta x, but if you imagined these being infinitely close together, then there would be no variation at all. So that's what we mean. So basically, the period is always, the k sub x, our spatial frequency is always 1/, the spatial period of repetition, okay? Okay, so this is just showing you sort of a plan view of the same thing, showing how basically we get different phases because the different spins over a certain amount of time change different phases. Those phases now give us information about the spatial variation. Okay, so let's go back to our phasor diagram, and let's go back to the definition of Fourier transform, right? If I have some object g of x, the Fourier transform of that is just I take g of x and I multiply it by this complex exponential. Okay. So what is that, a complex exponential? Well, it's just a phasor that has theta equals minus 2 pi kxx. So Yes. This one? This one? This one?
Yes. The bottom and those small regions always, but maybe they stand too fast. So
Sorry, the last row.
the last row, the small little mass also spins, but it has no effect.
Sorry, yeah, so this last row is essentially, yeah, they've all spun, but their net phase is all zero.
Okay.
So at that point in time, even though this guy was spinning around, he's gone back to zero. So what you care about is at every point in time, what is the phase, the relative phases of all the spins? Because at any given point in time, you don't necessarily know the history, right? You're just looking at this point in time and you're just looking at, where do these spins end up? So at the last row, after these 1, 2, 3, we've taken 4 steps of time. And with those 4 steps of time, we've ended up back at zero phase for all the spins. Okay. Okay, so basically we have phase is equal to minus 2 pi kxx, right? So basically the phase is varying with x, which tells us, oh, well, but the example we just did also had a phase that varied with x. So maybe what we just did is somehow related to the Fourier transform, right? It better be, otherwise we wouldn't have done the example. Okay, so let's look at what this is. So let's say we have kx equals 1 at x equals 0, 2 pi kx is equals 0, so theta equals 0, right? Now we go to x equals 1/4, so we go 1 unit there. 2 pi kxx equals pi over 2. So theta equals minus pi over 2. Okay, and then we can go x equals 1/2, and now we get theta equals pi or minus pi. It's the same. And then in this case, we get 3 pi over 4, or is that right? This should be 2, right? I think that's a mistake, right? Does anyone want to check that? Okay, 3 pi over 2, yeah. So this is equal to minus 3 pi over 2, right? And this also equals minus pi, okay? So basically, all it's saying is this thing that we need in our Fourier transform is a spatially varying phase, right? And we saw that in MR, we can get that spatially varying phase just by having spins processed at different frequencies, okay? So we'll look at the spins, and let's say, now we're going to look at things as a function of time, right? Remember, our experiment was we're looking at how the spins evolve over time, okay? So at time equals 0, we assume all the spins are in phase. So we start off, all the spins are in phase, and let's say that, so that means that kx equals 0, right? Because all the thetas are equal to 0, right? Right. So if kx is equal to 0, that means all these thetas are equal to 0. Okay. Now, going from here to here, so this has gone, let's say, minus pi over 4. This one has gone minus pi over 2. This one has gone plus pi over 4. And this one has gone plus pi over 2. Okay. Let me erase that. Let's see, whoops. Eraser here. Let's erase this point here. Okay, back to you. Okay, so this is at, now my claim is this is at kx equals 1 over 8 times delta x. Okay, so let's check that. If I look at this spin here, right, this spin is pointing exactly the opposite of this spin, right? So that's half a period, right? So this distance here from here to here is 4 delta x, okay? And that's equal to half a period. Okay, so we know that the full period here would be 8 delta x, and that exactly corresponds to my spatial frequency 1 over 8 delta x. All right. Now we let the spins evolve even more. Okay, so now in this amount of time, he accumulates a little more phase. So now it's gone minus pi over 2. This one has gone all the way minus pi. Okay. This one has gone plus pi over 2. And this one has gone minus or plus pi. And now look at the phase. This spin here is pointing exactly the same as this phase, right? Okay, so now my period is 4 delta x, right? And this corresponds to, well, this kx is equal to 1 over 4 delta x. All right. So the main point for today is by using gradients, we can get these phasor patterns that correspond exactly what we need for the Fourier transform. Okay, so at every point in time, these phasor patterns are the phasor patterns that the Fourier transform needs. Okay. Okay, so any questions on that? Okay, so we're going to spend the last 10 minutes reviewing 2D Fourier transforms because that's what we need. A lot of this was covered in the supplementary session. I'm just going to go through it a little faster now. So if you feel like you need some more review, there's that supplementary session. There's also there's like a Fourier transform playlist, at the course channel if you really want to dive into depth even more. Okay. But we'll cover the essentials here. So the idea is that we define the Fourier transform of a two-dimensional function by just multiplying it by a two-dimensional phasor and then integrating over dx dy. So we're going to talk about this term for now. Next lecture, we'll talk about how we do this actual integration. Okay. Luckily, that sort of comes for free in MR, so we don't have to worry about it too much. But basically, MR does both these things. It basically takes your object, essentially multiplies it by this phasor, and integrates. So it's pretty amazing that you're actually implementing the Fourier transform in your object itself. Okay. And then the idea is this is the data that we collect. This is what's coming off the MR scanner are these coefficients. So then we take those coefficients into our computer and then we compute the image. Okay, so that's what MR is doing. So reminder, we will use the term K-space quite a lot. That's sort of the standard in MRI. We talk about K-space as just our notation for Fourier space. So if you hear K-space or Fourier space, it's the same thing. So this is basically, you sort of see we have an image as a function of X and Y, and then the Fourier transform or the K-space representation is in terms of Kx, Ky. Okay, so those are the coordinate systems we'll use. You can sort of see here, for this object and almost any biological object, you can sort of see that the Fourier transform is pretty big. So the brightness here indicates how big the Fourier coefficient is. So as you sort of see, it's pretty strong at the center, and then it falls off as we go out to higher values of K-space. Okay. So the center of K-space is actually quite important. Okay. We actually just looked at this sort of property when we did the RF equation, which would say if I have g of x multiplied by some phasor and I evaluate it at 0 frequency, that's just the area under my function. Okay. For a 2D function, then it's just the area under gx gy. So basically, if I have any object with a bunch of protons in it, that's just sort of the summation of all those protons. Okay, without any dephasing. So that's always tends to be the largest value because that's just summing up all the protons in my object. Okay. So notice that for any biological object, now obviously we come up with a mathematical object where that would all cancel out. But in terms of any actual sample that has protons in it, there's not going to be any cancellation. So you're just adding up all those protons. So the Fourier transform always tend to be very big and then just fall off. Okay. Okay, so let's remind ourselves of what the 2D phasor looks like. Using Euler's theorem, once again, we can just say it's got a cosine and a sine term. But let's look at this in more detail. Let's take an example here where ky is equal to 0. Okay, so then this term here just becomes cosine 2 pi kxx. So this is a function that only has variations in the x direction, right? These green lines are showing sort of the peaks of the cosine, right? And it's got a period of 1 over kx. Okay. Similarly, if I took something along kx equals 0, then that term loses its x dependence and only varies with y. Okay. And if I have both kx and ky components, then I'm going to have variation both in the x direction and the y direction. So I'm going to have diagonal stripes. Okay. So the way to think about it is, if I'm in kx and ky, right? This is like a point here, right? So if I have some value, if some Fourier component along the kx axis, it's going to correspond to something like this. If I have some component along the ky axis, it's going to correspond to something like this. And if I have something out here, it'll correspond to something like this. Okay. So where you are, if you have energy at any point in Fourier space, it tells you about the pattern that it corresponds to. All right. And then the nice thing you can do is, I'm not going to go through all this algebra. It's good. You can sort of see the supplementary notes and stuff. But the key is that if I'm at any, say in the kx, ky domain, okay, I'm at some point in k space, okay, and I'm at some angle theta. It turns out that this angle theta is the same as this angle theta, which means my wavefronts are just perpendicular to that. Okay. So if you're at any point in k space, you know what the pattern is by just drawing perpendiculars to that direction vector. Okay. It also turns out that this here, Pythagorean theorem, obviously has some magnitude kx squared plus ky squared, right? And 1 over that gives you this period here. Okay. So if I take 1 over kx squared plus ky squared, that's the period that you have. All right. Okay, so let's do an example. So that's showing if I'm at some point along the kx axis, it's got x dependence. If I go farther out in k space, I'm at a higher spatial frequency, right? So the period has to decrease. If I go along the ky axis, I only have patterns that have a y dependence. If I go further out, then that spatial period decreases. Okay. And if I go somewhere along the kx, ky axis, now I have diagonal patterns. All right. Now we're going to talk about sort of, I'm going to play this movie. So it's here you're seeing k space. And here you're going to have the image. Okay. And the idea is that right now I only have the center of k space, right? And so you sort of see I have a fairly blurry image, right? I only have information about very low frequency spatial components. And as I play it, I'm incorporating more and more of k space, and you can sort of see the details are filling in. Okay. So the basic idea is that the center of k space really tells you the overall brightness of your image and sort of very low level details. And then as you incorporate more and more of k space, you start filling in the details. Okay. So when you're looking at, so this is going to sort of introduce us to some of the trade-offs we have to make. Is one of the design decisions we have to make in MRI is how much of k space do I want to collect? Like, is that enough k space, or do I need to collect this much k space, or is this enough k space? Okay, and you can sort of see that how much we collect in k space is going to have a direct effect on our resolution. Okay, so the less information I collect in k space, the lower resolution my image is going to be. The more information I collect, the higher resolution image is going to be. But the trade-off is it takes time to collect more data. Okay, so that's the trade-off. Like, I can go out and collect more k space, but it's going to take more time. Okay. Conversely, I can acquire image very quickly, but it's not going to be very high resolution. So that's one of the trade-offs we'll make. Yes.
But k-space data is two-dimensional.
Yes. It's a function of kx and ky. Yeah. For 2D Fourier transform, it can be n-dimensional, you know, if you're talking about an n-dimensional Fourier transform. Yeah. But for this class, we're going to stick with 2D. Okay. So in the last minute, let's just look at this example here. So this is the image. This is its Fourier transform. And here I basically zeroed out these parts of k space. Okay. So remember, the information that would be represented by these components are like these vertical stripes. Okay. So let's look at our image and see what happens to the vertical stripes. So for example, here, you're noticing that this edge here, it's pretty sharp, right? We have a pretty sharp delineation of that edge, right? If I go here, notice how that edge has got blurred out. Okay. Whereas here, if I look at a horizontal edge, it's pretty sharp. And here, it's still relatively sharp. Okay, because I've kept the information about these stripes, but I've lost information about those stripes. Okay, so that's it for today. We will continue this on Wednesday, and there'll also be an additional pre-lecture quiz probably posted later today that will be due 10 a.m. the day of on Wednesday. Okay, so I'll stick around if there's any questions about homework or anything else.